Chapter 1, Part 2. We're going to be looking at conversions and density. First, we need to talk about measurements. So measurements are determinations of physical quantities. So there are several different types of measurements, but the four fundamental physical quantities are length, mass, time, and electric current. These four fundamental physical quantities can be used to express all other physical quantities, and we'll look at some of those. The most important thing with measurements is the units. So make sure you are always writing units when you are solving problems. If you give me a number without units, it means nothing. Because if you said 6.2, for instance, 6.2 what? Centimeters, inches, meters, those are all wildly different lengths. So the units define the number itself. Here in the US, English units are most commonly used. Feet, pounds, etc. Pretty much every other country uses metric units like the meter, kilogram, so on and so forth. This poses a problem when we're trying to share information in the science and math fields. So standardization was needed in order to share and communicate our developments with each other. So in 1875, in Paris, France, the Treaty of the Meter was signed, and this developed a common standard for length, mass, time, and the other physical quantities. Since the metric system was already in use in most other countries, it was the metric system that was adopted for this standardization. It's called the International System of Units, SI units for short. What I have below is a table with the four fundamental physical quantities that we talked about on the previous slide and the corresponding SI units that are used. So these are the units that everyone uses in the science and math field when expressing measurements in length, mass, time, and electric current. So for length, the units that we use are meters. For mass, it is kilograms, kg for the abbreviation. Now in physics, which is what we're going to be looking at in the first several chapters of this course, kilograms is most often used when we are talking about mass. However, when we get into chemistry towards the end of the semester, we'll be talking about grams and milligrams more often. It's still a metric unit, just a different prefix. We'll talk more about prefixes with metric later on in this PowerPoint. So for time, we're using seconds, abbreviated with just the letter S. When we get into electric current, which is going to be a few chapters from now, that will be measured in amperes. Here's a more inclusive table that includes more than just those four fundamental physical quantities. So you can see them represented as the first four in the table. I wanted to include a few more because we'll see those in later chapters. So temperature, for instance, we will be measuring in Kelvin. We'll also talk about how to convert between Celsius, Fahrenheit, and Kelvin. For the amount of a substance, this will apply when we talk about chemistry. The units that we will use to talk about an amount of a substance will be the moles, M-O-L. Luminous intensity is probably the only unit of measurement that we'll not cover in this course that is included on this table. So now that we know about measurements, let's talk about conversions. So what a conversion is the change in the form of a measurement. So different units. We're not actually changing the amount, we're just changing the units themselves. And to change the units, oftentimes the numbers are going to change. So in order to convert, a conversion factor is usually needed, especially when we're doing English to metric conversions. And what a conversion factor is just a number that we use to change one set of units into another. And we do this by multiplying or dividing. So you can see in the example below what we're trying to do is convert 5 kilometers into miles. So if you've ever thought about running a 5K or have run a 5K before, you might have wondered exactly how long that is in miles. So in order to figure that out, you would need a conversion factor, which is in yellow. The conversion factor we're going to use to convert 5 kilometers to miles is 1 mile is equal to 1.6 kilometers. So to figure this out, we're going to take that conversion factor, and in this case you'll notice that we put the 1.6 kilometer part of that conversion factor in the denominator. We represent the conversion factor in a fraction form, putting the kilometers on the bottom so that the kilometers cancel out once we do the calculation. That leaves our units, once we're done with the calculation, as miles. So in order to figure out how many miles there are in 5 kilometers, we take 5 divided by 1.6. That gives us 3.1 miles. Let's look a little closer at conversion factors. You'll notice from the previous slide and the example shown here that conversion factors are written as an equation. So the one I have shown here is 1 yard is equal to 3 feet. So since it is written this way, we can actually represent that conversion factor in 2 different ways. So whenever we are doing a conversion, calculating, we always write the conversion factor as a fraction. And we can represent that fraction in 2 ways. The first way that I have shown here, we have the feet portion on the bottom and the yard portion on the top. Or we could flip that fraction, leaving the 3 feet in the numerator and the 1 yard portion in the denominator. Either way, we're going to pick the way that best applies to the conversion that we are trying to calculate. So let's look at an example and how we would use conversion factors. So in this example, we're asked to convert 0.75 quarts to liters. So in order to do that, you're going to need to look up on a conversion factor sheet some conversions. Now, there are several different conversion factors that will get you there, and it really doesn't matter which ones you choose. As long as you are crossing out what you don't want and keeping what you do, you'll get the correct answer no matter the conversion factor. So the 2 ways that I have shown here, the first way we're going to solve it is we're going to use 2 separate conversion factors. So you'll notice we're trying to get from quarts to liters. So this first conversion factor that I'm underlining here will get us from quarts to gallons. The second conversion factor next to it will get us from gallons to liters. So I'll be using 2 conversion factors to get to liters. So let's see how that looks. When we start a conversion factor, when you see me do some on the board, I'll draw what I call railroad tracks. So a horizontal line straight across and then vertical lines separating the conversion factors being used. So you always start your conversion by putting the number given in the problem itself in the upper left-hand corner. So that 0.75 quarts is how we're going to start our problem. Next, you're going to take your first conversion factor and place it in the slot next to it. So the first conversion factor I'm using is the 1 gallon is equal to 4 quarts. Now I'm going to represent this as a fraction, putting the 4 quart portion on the bottom in the denominator so that my quarts are on opposite sides of that horizontal line. That horizontal line represented there is actually a division. It's dividing. So if I have units on opposite sides of that horizontal line, they can cancel each other out. I put the quarts on the bottom so they cancel, and then the 1 gallon portion in the numerator so that when I do this calculation, it's gallons that I'm keeping. So if I were to stop in this very first step, what I would have is my answer in gallons. But I don't want it in gallons, I want it in liters, so that's where the second conversion factor is going to help. So in this case, I'm going to take that second conversion factor and I'm going to put the gallons in the denominator this time. That way, gallons are on opposite sides of the horizontal line, canceling each other out. The 3.78 liters is going to be in the numerator because liters is what I want my final answer to be in. So now to calculate. I said this horizontal line is a division line. Well, the vertical lines are multiplication. So you want to multiply all the way across in the numerator and the denominator. So to solve, we're going to take 0.75 multiplied by 1 multiplied by 3.78 and divide that by 4. The answer the calculator comes out with is 0.70867. Now we need to take into account significant figures. That's why we learned about them in the first part of the chapter. To figure out how many significant figures you need to report your answer in, you're going to look at the original problem and count how many significant figures were in the number given in the original problem. So 0.75 was the number given in the original problem, and that has 2 significant figures. So since there are 2 significant figures in the number given in the problem, we want 2 significant figures in our answer. So to do 2 significant figures, start counting at the 7, and the 0 is going to be your second significant figure. Look to the number next to it. It is an 8, so we're going to round up to 0.71. Now notice when I was taking into account significant figures, I did not look at the conversion factors and use those to help me figure out how many significant figures. The conversion factors do not matter. They don't count towards significant figures. If I used the conversion factors to count towards significant figures, I would have only had 1 significant figure in my answer. So do not use the conversion factors when you are trying to figure out how many significant figures should be in your answer. Conversion factors are what we call exact numbers and are not used. Okay, now let's look at another way we could have done the problem. So say you found a different conversion factor than the ones I used first. Say you found a conversion factor going directly from quarts to liters. So 1 quart is equal to 0.946 liters. So if you were to use that conversion factor instead, you would still get the same answer as I have shown below, and you would actually get it in just 1 step instead of 2. So looking at that, notice I'm starting again with the 0.75 quarts. You always start with what's given in the problem. I then am multiplying that by 0.946 liters because I want the quart portion on the bottom in the denominator so that it cancels. Multiplying that out, I get 0.7095, but once I factor in my significant figures, I actually get the same answer, 0.71 liters, that I did in the other conversion, using different conversion factors. So it doesn't matter which conversion factors you use, as long as you are setting up the equation correctly. Let's look at another example. This would be a conversion that you would actually do in your everyday life, and you might have even done a calculation such as this before and not thought of it in a conversion factor way. So the question is asking, how much would the gas cost for a round trip to Dallas, Texas? Well, you need to know how far away Dallas is. You'd also need to know the miles per gallon that your car gets and the cost of gas. So I have all that written here. So how do we do the problem? Well, you start with the distance. So we're going to start with 318 miles. Notice we're multiplying it by 2. This is because Dallas is 318 miles away, but the question is asking for a round trip. So we need to come back as well. So it would be twice the distance. So 2 times 318. Next, we're going to use the miles per gallon and the cost of gas as conversion factors. So if your vehicle gets 33 miles per gallon, that's actually a conversion factor because it's saying that you have 33 miles is equal to 1 gallon of gas. So now it's written like a conversion factor, and what we can do is represent it as a fraction in 2 different ways. And we're going to choose to have the fraction with the 33 miles in the denominator. We do this so that the miles are on opposite sides of that horizontal line and they cancel. We then have the 1 gallon in the numerator. So if I were to stop at this step, I would be calculating how many gallons it's going to take to get to Texas round trip. But I don't want to stop and know just the gallons. I want to know the cost, how much money it's going to cost me. So that's where the cost of gas is going to come in handy. We're going to use that like a conversion factor as well. So if gas were $2.34 per gallon, so that means $2.34 equals 1 gallon. So that's our conversion factor. We represent it in a fraction form, putting gallons in the denominator so they're on opposite sides of that horizontal line. Now we can calculate. Remember, you're multiplying across, so we're going to take 318 times 2 times 1 times $2.34. We're then going to divide that by that 33 miles. What we end up getting is 52.3898. Rounding to 4 sig figs, it's going to cost us $52.39. So here are some conversion examples that we're going to work through in class. These are all English to metric conversions or English to English conversions. So they're going to require conversion factors, and I'll post a conversion factor handout on Blackboard for you to use. Now let's look at metric to metric conversions. So metric to metric conversions are actually quite nice. Since most science and mathematical fields have adopted the SI unit so that we can share information with each other, it's the metric system that's most often used. And the nice thing about the metric system is you don't necessarily need a conversion factor to convert from metric to another metric unit. All you need to do is move the decimal point. So when it comes to the metric system, the numbers itself are going to stay the same when you're converting. It's where the decimal is that's going to change. So what I have below are some metric to metric prefixes. So we're going to focus on just a small portion of metric prefixes from kilo down to milli. So what I have represented here, this K, H, D, blank, D, C, M, those letters are representing prefixes, metric prefixes. The K is for kilo, the H is for hecto, that first D is for deca, the second D is for deci, the C is for centi, and the M is for milli. You're going to want to remember this arrangement of letters. So some mnemonic devices that might help you remember, the one I use is kiss her dummy blank don't chase me. Noticing that the first letter of every one of those words represents the arrangement of prefixes on my table. Another one that you might have heard before that's very common is King Henry died drinking chocolate milk. So the reason we want to remember this is because this gives us the order of the prefixes, and when we move the decimal point, by knowing what letter we want to start at and what letter we want to get to, that'll tell us how many spaces to move the decimal. And I'll work through an example here in a minute so you can understand more fully what I mean by that. Before I work through the example, I want to talk a second about this space, this empty blank space. So that's what we call our base. So the reason that there's a blank space there is because you're going to put a letter there depending upon what type unit of measurement that you're converting. So for instance, if you are dealing with length, what's going to go there is an M for meters. If you are dealing with mass, what's going to go there is a G for grams, because that's the metric unit for mass. If you are dealing with time, we're going to put an S there for seconds. If you are dealing with volume, you're going to put an L there for liter. Okay, so it's an empty space because it applies to several different types of units of measurement. Now notice over on the right, I have a table of a lot of the metric prefixes. It's not all of them, but it's most of them. And notice we're just using this very small portion from kilo down to milli. So that's all we're going to cover in this class. We're not going to go any higher or any lower than that. So let's look at some examples. I'll be working through this on the videos of class, but I wanted to point out one example at least to show you how we're going to be using that scale that was on the previous slide. So remember, it's KHD space DCM. So I'm just going to work number 4 here for you using this KHD DCM. So when you're approaching a metric to metric conversion problem, you need to first see what physical quantity that you are converting. So in the case of number 4, we are converting 0.12 seconds to milliseconds. So we're doing time. So time, more specifically, the units we're using are seconds. So what's going to go in my empty space is an S. Now to convert from seconds to milliseconds, we said for metric to metric, all we're doing is moving the decimal point. So according to this chart, I am starting at seconds, so I'm starting at the S, and where do I want to get to? I want to get to the M because I want to go to milliseconds. So to figure out how many times to move the decimal, I am going to stop at every prefix letter and count that as one spot. So to go from seconds to milliseconds, I'm going to move the decimal once to get it to deci, 2 times to get it to centi, and 3 times to get it to milli. So now I know how many times I need to move the decimal. I'm moving it 3 times. Okay, well, what direction am I moving it? The same direction I just moved it to get to milli, to the right. So I'm going to come up here to this 0.12 seconds. I'm going to start at my decimal, and I'm going to move it 3 times to the right. 1, 2, 3. What's going to go in that empty space is a 0. So 0.12 seconds is going to equal 120 milliseconds. So all you have to do is just move the decimal point. We'll work through more problems during class. Experimental error is the next topic we're going to cover. An experimental error is your percent uncertainty. We're going to use this a lot in lab, where you need to calculate the percent error based off of your measured experimental results and the actual or true results. So you can see by the equation in yellow here that you're taking your measured results, the experimental results, the ones that you get during lab period, and you're going to subtract it from the true value, the actual value. Notice that subtraction has bars around it. What these bars are called is absolute value bars. So when you do that subtraction, if you get a negative number, you want to make sure that you change it to a positive. You don't change the number at all, you just change the negative sign into a positive sign. So you take your measured minus true, and you're going to divide it then by the true value or the actual value. The main mistake that people make when using this equation is not doing the subtraction part first, or at least putting that subtraction part in parentheses in your calculator. If you don't put it in parentheses in your calculator, what's going to happen is that it's going to do the division portion first by orders of operation, and then you're going to get the incorrect answer. So just make sure you're doing that subtraction first or putting it in parentheses in your calculator before you divide by the true value. Don't forget to multiply by 100 to make it a percent. So an example that you might see using the experimental error calculation would be this word problem below. So the word problem is saying that a student dropped an apple from a distance of 2 meters and it took 0.62 seconds for the apple to hit the ground. That's what they recorded. The theoretical time it should take based off of gravity is 0.64 seconds. Calculate the percent error. So how far was the student off from what the value should have been? So you're going to use that equation on the previous slide. What you need to figure out is which of those numbers is the measured and which one is the true, so that you're putting the numbers in the correct spot and calculating the percent error accurately. So to figure that out, use clues from the word problem. So the measured part, that is always the experimental. That's what the student or the scientist is getting when they record results. That's their data. So the measured in this word problem is going to be the 0.62, what the student recorded. The true value is going to be the actual, the theoretical value, the proven value, the value that you would get from a table. So the 0.64 is going to be the true, what you will insert the true in that equation. And a clue to figure that out is this word theoretical. The theoretical time is 0.64. So you take those numbers, plug them into the equation on the previous slide, multiply by 100 and solve. We will work through this problem in class and a few other experimental error calculations. The last equation we're going to look at in this chapter is density. And what density is an object's mass divided by its volume. So the more dense an object is, the heavier it is. For instance, if you were to mix water and oil portion would float or be on the top of the water. And this is due to its density. Water has a higher density than oil does. So water is going to sink towards the bottom of the glass and the oil is going to rise to the top of the glass. When we're using this equation, we're taking mass divided by volume, and the mass portion is going to be in grams. The volume portion is going to be either in centimeters cubed or milliliters. Now they're interchangeable because 1 centimeter cubed is actually equal to 1 milliliter. The reason we have both units is because centimeters cubed is most often used when we are talking about solids, aluminum, iron, copper, etc. Milliliters is going to be more often used when we are talking about liquids because we often measure liquids in milliliters. The units, therefore, on density are going to be grams per centimeter cubed or grams per milliliter. It's important to know what the units are going to be because you need to make sure you're including units once you're finished with your calculation. Remember, a number means nothing without the units. Water sets the baseline by being 1 gram per centimeter cubed. So the density of water is just 1. So let's look at how we're going to do these calculations. What I have shown here is called the density triangle. And a lot of students prefer to use this triangle when they're doing density calculations because you're not always solving for density. Sometimes you're going to be solving for mass, sometimes for volume. And in order to solve for mass or volume, you're going to need to rearrange the density equation, and this triangle makes it easy to do that. So the triangle is DMV with the M portion in the top of the triangle. So how are we going to use this triangle? First, you need to look at the word problem and figure out what are you solving for? Mass, density, or volume. Once you know what the unknown is, you're going to cover that quantity with your hand. So if I were solving for volume, for instance, I would cover the V with my hand. Then I'm going to perform the necessary calculations indicated by the triangle. So just like when we're doing conversions, a horizontal line means divide. Vertical lines mean multiply. So if I cover the V, the triangle tells me I need to take the mass and divide it by the density to solve for volume. If I needed to solve for mass, for instance, I would cover the M with my hand, and I would take density and multiply it by volume to solve for mass. We'll be working through some problems on the board in class. There'll be a separate video for that, and I'll use the density triangle for those problems. So here are a few of the problems that we will be going over in class. These are all using the density equation or the density triangle. Some of them are solving for density, others for the mass and volume portions where you'll need to use the triangle or rearrange the equation. That is all for Chapter 1.